Hello and welcome to the third and the last part of our thermal energy storages lecture. This time we will talk about thermochemical heat storage. In principle, every chemical reversible reaction is an energy storage system. Depending on the temperature, a chemical reaction goes into both directions, so it is reversible. Discharging occurs at a temperature below equilibrium temperature. This is the exothermic reaction, and the charging occurs at temperature above the equilibrium temperature. That is then the endothermic reaction. Additional to chemical reactions, also the absorption and the adsorption processes are called the thermochemical energy storages. When we have absorption, that means a storage of a molecule that is intercalated into the absorbent phase. In this process, the absorbate is a soluble material dissolved into a solvent that is called the absorbent. As no chemical processes occur, the absorption is not a chemical process, and so strongly seen it's not really a thermochemical storage. It's a dilution process. Absorbents are solid, microporous materials. The energy storage density with absorption is determined by the molar mass of the absorbent, the affinity and aggregate state of the absorbent, and by the absorbate. Examples are for that lithium bromide, which is then the absorbate, in water, which is the absorbent, or ammonia as the absorbent, also in water, which is then the absorbent. Adsorption, that means the physical accumulation of molecules, which are then the absorbate, on the surface of a usually porous adsorbent. Unlike the chemical reactions, there is no defined equilibrium temperature. The heat released is determined by the varying binding energies at the accumulation sites in the adsorbent. Here the storage density of an absorption storage system is determined by the adsorbent's evaporation enthalpy, the binding forces between the adsorbate and the adsorbent, and by the lift in charge between the charging and discharging temperatures. Examples here is, for example, silica gel, which is then the adsorbent with water as the adsorbate, or zeolites as the adsorbent, again in water as the adsorbate. How are such heat energy storages constructed? The materials must also be separated or exchanged at the same time heat is added or removed to those systems. And therefore we can distinguish sealed systems or open systems. In sealed systems are generally airless systems with a vacuum seal that permit gaseous components of any kind to be used. Very low pressures in the vacuum are required for the reaction, but the gaseous components must be stored in the system after the charging process. And therefore the components in the picture called or signed with B can be condensed and therefore reduce the volume required for the storage tanks. For the reverse reaction, then the components B must be vaporized again, and this process requires ambient heat. This evaporation process largely determines the usable energy or power of the storage facility. Open systems. In open system, components must be present in the atmosphere. They are released during the charging and then absorbed or reabsorbed during the discharging process. On the left side here we see the fixed bed designs that are the most commonly ones today. The adsorbent is in the form of a fill here. The adsorbate, usually water vapor, flows through it ambient pressures. Other reactor designs exchange a mass flow of solid or liquid sorbents that we see in the middle and on the right side with the adsorbate flow. The advantage of these reactors is that power and storage capacity are decoupled and can be designed separately from each other. The power is determined by the size of the reactor, but the capacity is determined by the size of the sorbent storage containers. With open adsorption systems, no storage at all is required for the gas components B inside the storage system. Ideally, they are components of the atmosphere that can be temporarily stored in the ambient air. This increases the energy storage density by share of volume subtracted that was used to store the gas components. Here we see an example of a thermochemical storage and adsorption process that uses zeolite and water. And when we start here on the right side with the charge of the storage, that means we need to provide heat energy to the storage systems in form of a warm but dry air flow. And with that heat we can separate the zeolite and the water vapor. And what is then released by the storage is then a cold but saturated, vapor saturated flow of air. When we later want to discharge the storage, then we have a cold and wet air flow that we put into the storage, and then the vapor, the cold vapor, is intercalated to the zeolite, and as a consequence the storage releases heat. And what is going out of the storage is then a warm or even hot and dry airflow. One practical example where it is applied nowadays is, for example, energy and water saving dishwashers. And that we will see here explained a bit more in the next video. Hi, my name is Flashy, and today I explain something about thermochemical heat energy storages. Thermochemical heat energy storages can be distinguished into two types: absorption and adsorption. With absorption, the absorbate is solved within an absorbance. Here the absorbate gives energy to the absorbance. With adsorption, the adsorbate is intercalated into the surface of a solid medium, the adsorbance. Also here, heat is exchanged. I will demonstrate the practical use of adsorption. With traditional dishwashers, a heating system is used to dry the washed dishes. With me, that is different. Within my stomach, I have a zeolite storage. It is located in my bottom. Zeolite are crystalline silicates. They exist in the nature, but also can be fabricated synthetically. They have a very big specific surface. That is how I look when you cut me in two halves. Cold liquid air is the blue arrow on the left side. The zeolite storage is at the bottom on the right side. With the help of a fan, wet air is blown towards zeolite storage. Water is intercalated in the zeolite. Under the microscope that looks like that. The zeolite offers sufficient possibilities for water molecules to be intercalated. Zeolite and water generate heat. Cold air is heated up and dries the wet dishes. This is the charging process of the thermochemical storage. When this process is finished, the storage contains water. With the next operation of the dishwasher, this water can be reused again. As a consequence, water is saved. and also electricity is saved, as during the drying process no energy is needed. Okay, and let's end like always with some questions for the self-monitoring. First, describe the function of sensible heat storage, describe the function of latent heat storages, and describe the function of thermochemical heat storages. Which are the boundary conditions that decide on the capacity of a sensible heat storage? What are the main points to take care for seasonal heat storages? Which are the most important characteristics of thermochemical heat storages? Thank you very much. Bye bye.